Hello friends, welcome to GT Science tutorial. In this video, I'm going to explain about the ideal gas behavior, and in this topic, we are going to study about all these 7 laws. If you are a chemistry or physics student, then you must be familiar with these terms. So what are the meaning of these terms individually? In this video, we will understand about everything. So let's start. First of all, we need to understand about gases. So we know that if we take number of atoms and if they are arranged in an order and if the force of attraction between them is very strong, then they will form a rigid body that is called a solid. Now if we heat a solid, then these intermolecular forces of attraction will be weaker and these atoms will go little far and it will not have fixed volume. It will not be rigid and they are called liquid. Now if we heat it further, then the atoms will go very far from each other. There is no force of attraction between them as well and there is no fixed volume as well. No fixed volume as well. Now this is called gas. Now if we further heat it, we will get plasma, but that is not the concern topic right now. We are just going to talk about gas. And gases are of two types. They are ideal and real. So ideal gases are those gases which obey all those laws. Which laws? These laws, which obeys all these laws at all temperature and pressure. So obeys all the laws. And real gases are those which obeys these laws only at low temperature, low pressure and at high temperature. High temperature. Only at these two conditions, the real gases obeys all those seven laws. Otherwise, they won't obey at all. And those gases which obeys all the seven laws at all conditions are called ideal gas. So our concerned topic is to study about ideal gas right now. Okay. Now let's start the laws. The first one is Boyle's law. Boyle's law. Now this is the most talked topic you will ever see in gases chapter. So in 1660, a scientist named Robert Boyle. In 1660, a scientist named Robert Boyle found out that the pressure and volume are interrelated. What he did was he took a piston. What he did was he took a vessel like this and he took a piston over here. This is the movable piston. Okay. And he kept some gas molecule over here inside the vessel. And he pushed the piston downward in order to increase the pressure, or you can say decrease the volume. And what he found was the pressure inside the box increased, vessel increased. And similarly, when this piston moved up, then the volume increased, and he found that the pressure decreased. So he formulated a law that is at constant temperature, the pressure the pressure of a gas the pressure of a gas is inversely proportional to its volume. So this is the law that Boyle gave. At constant temperature, the temperature should be constant. The pressure of a gas is inversely proportional to its volume. So mathematically, what do we see? Pressure is inversely proportional to volume. So this is the law that he gave. Okay, and this is at constant constant temperature. Now, if we take this volume to this side and if we remove this proportionality sign, then in right hand side there will be a constant. So it will be PV is equal to constant. Okay, let's consider this to be equation number 1. Now let's consider two cases. P1 pressure at volume V1 and P2 pressure at volume V2. Okay, P1 at V1 and P2 at V2. Then what do we see? This equation. This equation will now become P1 V1 is equal to constant constant when the pressure is P1 and volume is V1. This is equation number 2, and P2 V2 is equal to constant constant. This is equation number 3. Now this is when we get when pressure is P2 and volume is V2. Then if we combine these two, there is constant in the right hand side. So left hand side will also be equal. P1 V1 is equal to P2 V2. Now this equation is used in a lot of numerical problems that we will see in our future videos. Okay. Now we need to talk about certain graphs. We need to talk about certain graphs that we find in Boyle's law. Okay, so we see that Boyle's law states that at constant temperature, the pressure and volume are inversely proportional to each other, right? Inversely proportional to each other. Now look at here. So if we plot a graph, when pressure whose unit is ATM is in y-axis and volume in x-axis, then we get a curve like this. So as volume is increasing, the pressure is decreasing. Okay, so this is the typical curve that we get in Boyle's law, and the curve's nature is a hyperbolic. So I hope you understood it properly. Now let's move forward to study about the Charles law. Now let's talk about the Charles law. Charles' law is little complicated as compared to Boyle's law. So in 1787, Charles studied a phenomenon. What he did was, he took a he took a vessel like this. He took a vessel like this, and at constant pressure, he put a gas. Now, to maintain a constant pressure, he put a fixed lid over here. It is immovable, not a piston. Okay, so this provides us a constant pressure environment. This provides us a constant pressure environment. So what he did was, he observed the volume of the gas increasing or decreasing with temperature, and he found out an interesting phenomenon. Okay, so he found out that the volume of the gas, increases or decreases. The volume of the gas increases or decreases by 1 by 273.16 of its value at 0 degrees Celsius. So he found out this: the volume of the gas either increases or decreases by a factor of 1 by 2.7, not by a factor, by 80 of its volume at 0 degrees Celsius. So if this is the gas, okay, these are the gas. This looks like water, but this is gas. Okay, now if we put it at absolute zero, then it will have certain value of volume, right? Now if we increase if we increase the temperature, the volume of the gas will increase by this much of the volume at absolute zero. So this is the meaning of Charles law. Mathematically, if we write it, we get a formula. Now for that, at constant sorry at 0 at 0 degree Celsius, let us consider the volume B is equal to V naught, and at certain temperature, at certain temperature T, the volume becomes Vt. Then we talk about this certain temperature. Vt is equal to, this will be Bo plus, that is the volume at absolute zero, plus T by 273.16 into V naught. T by 273.16 into V naught. This is the formulation for Charles law. That is, the volume is increasing by 273.16 degree of this volume at absolute zero. And if we take VO constant from both of them, then we will get 1 plus T by 273.16 VO 273.16 plus T by 273.16. Now you can see this is a constant value. At certain temperature, this becomes a constant value, right? Now, uh, now we can write it like this. So Vt is equal to Vo into the upper temperature T plus 273.16 degree. This is for the absolute zero at Kelvin scale, and adding some temperature, it will give the temperature in degree Celsius. Okay, it will give the temperature in degree Celsius, and this is TO, means absolute zero at in degree Celsius. No, in Kelvin temperature. And this is also in Kelvin temperature. Okay, sorry for that. Now, if we add some degree Celsius temperature with 273.16, this will give the value in Kelvin temperature, Kelvin scale. So we get this value. Now this is the final expression for Charles law. Similarly, now this law will give us a very important equation that is used in numerical problem as well. And that equation is V2 by V1 is equal to T2 by T1, because T1, because this equation tells us that as volume increases, the temperature increases. So V is directly proportional to T. This is the main gist of this whole Charles law. Now if we try to plot a graph, if we plot a graph like this, and in the y-axis there is volume, in the x-axis there is temperature, that is in Kelvin scale, then we get a curve like this, like this. So the line passes through the origin and its slope keep on increasing in positive direction. Okay, and these type of curves are called isobar. So I hope you understood about Charles law. Similarly, we can establish another relation relating pressure and temperature, and this will give us pressure is directly proportional to temperature as well. At temperature increases, the pressure will increase, and at temperature decreases, the pressure will decrease as well. So this is very simple one, right? Now let's move forward to see Avogadro's law. Now let's talk about Avogadro's law. Avogadro's law. Avogadro's law is by far one of the simplest. So what he considered was at constant volume, at constant volume, at constant volume, temperature and pressure. So if we take constant temperature, volume and pressure, but two different gases, A and B, they are two different gases, then the number of moles of these two gases will be same. Number of moles of A and B are same. So at constant volume and temperature and pressure, the number of moles of these two gases are same. So the gist of this Avogadro's number is at constant temperature, pressure and volume, 1 mole 1 mole of any substance contains 6.023 into 10 to the power 23 number of atoms. Okay, so at constant temperature and pressure, any gas molecule, 1 mole of any gas molecule will contain 6.023 into 10 to the power 23 number of atoms, and this is denoted by an A. Whenever you see Na, you need to understand its value is this much, and this is the Avogadro's number. So it is 6.023 into 10 to the power 23. Okay, so this is very simple, isn't it? Now let's talk about another law. The fourth one is equation of state of an ideal gas. Equation of state of an ideal gas. Equation of state of an ideal gas. Here we are going to talk about the ideal gas equation. Ideal gas equation. Ideal gas equation is very important equation because this relates pressure, volume and temperature. Okay. So from Boyle's law, what do we see? Pressure is proportional to 1 by V, or we can write it like volume is proportional to 1 by T, 1 by P. Consider this to be question number 2. And from Charles' law, we see volume is proportional to temperature. Now combining these two, what do we see? In the left hand side there is V proportional, in the right hand side there is 1 by P into T, so it will be T by P. If we remove this proportionality sign, then we need to put an equal to and T by P into constant, right? Constant. If we take this P and T to left hand side, then we get PV by T is equal to constant. So we get an equation like this, right? Now, so at STP, that is at standard temperature and pressure. So at STP, pressure is 1 atm. 1 atm. Temperature is 273.16 Kelvin, and the volume occupied by any gas is 22.414 liters. 22.414 liters. So at that time, this value will give us a value equal to this value. Okay, PV by T will give us the value equal to N into R, where N is number of moles. And this R is a constant. This is a constant called the universal gas constant. So this equation PV by T, this equation will become PV by T is equal to N into R, or if we take this T to other side, this will give us PV is equal to nRT. This equation is called the ideal gas equation. Ideal gas equation. Here this P is pressure, T is temperature, V is volume, R is universal gas constant, and N means number of moles of the gas. Now we need to talk about this R as well. So what is the value of R? If it is a constant, it must have certain value. Let's talk about its values. Okay. Numerical value of R. R means universal gas constant. Numerical value of R, where R is the universal gas constant. So if we find out the value of R from ideal gas equation, then it will become R is equal to PV by NT, right? PV is equal to nRT is the ideal gas equation. Now let's put the values at STP. So what do we get? At STP, the pressure value is 1 atm into volume value is 22.414 liter by N means 1 mole into T means 273.16 Kelvin. And if we calculate it, then we get a constant value that is 0.0821 liter atmosphere, liter atmosphere per mole and per Kelvin. So we get this value. This is the value of R. Now in numerical problem, we might see different unit system. So at different unit system, the value of R is different as well. Now if we talk about another value, then R becomes 1.987 calorie per Kelvin per mole. Similarly, this becomes 8.314 joule per Kelvin per mole, and similarly it becomes 8.314 into 10 to the power minus is 10 to the power 7 arc per Kelvin per mole. Now these are different unit system and different values. Okay, so I hope you remember all these values along with the unit, because in numerical problems sometimes it will talk about liter, atmosphere, mole and Kelvin. Then you need to put this value 0.081, and if sometimes it talk about joule, the energy is given in joule per Kelvin per mole, then we need to put 8.314 as the value of R. Now, if we want to convert about this joule to calorie, we need to divide by 4.184, because in 1 calorie there is 4.184 joule. Okay, so it is very simple to convert this joule system to calorie system. So these are some different values of universal gas constant, and these are the corresponding units. Okay, you need to remember all these for numerical problem. Now let's move forward. Similarly, the fourth one is Dalton's law of partial pressure. So let's try to understand about this law. Okay, suppose we take a vessel like this. We take a vessel like this. Now we are putting gases over here, gas molecules, and all of these molecules are different and they are non-reacting gases. Okay, these are the non-reacting gases. These are the non-reacting gases that is put in the vessel. So according to Dalton's law of partial pressure, all these molecules will exert their own pressure. All these molecules will exert their own pressure. That is called the partial pressure. So we considering a number of non-interacting or non-reacting number of non-reacting gases in a vessel, then then the pressure then the pressure exerted then the pressure exerted then the pressure exerted by each gas is called is called the partial is called the partial pressure of that gas. So this is a very simple definition, right? I'm sorry, my handwriting is not that good. I'm still working on my handwriting. Okay, so if we consider P1, P2, P3, P4, to Pn to be the partial pressures of all the individual gases, then the total pressure P will be P1 plus P2 plus P3 plus Pn, and this can be written as summation I is equal to 1 to n pi. So this is the formula for the partial pressure. It's not that much difficult, right? Now let's talk about Dalton's laws special case. Okay, so for all these gas molecules, ideal gas equations can be applied. So we get applying ideal gas equations, ideal gas equation to all the molecules, then what do we see? P1 is equal to N1 RT by V, P2 is equal to N2 RT by V, P3 is equal to N3 RT by V, and Pn is equal to N RT by V. So we get all these individual equations. And if we put these values over here, then what do we see? Then total pressure P will be equal to, if we take RT by V common from all of them, then it will give RT by V into N1 plus N2 plus dot 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 Nm. So we get these equation. And if we add all these number of moles, and if it gives us anti means total number of moles, then it will be P is equal to anti RT by V, and this will give us PV is equal to anti RT. So we apply ideal gas equation like this in Dalton's law of partial pressure. Now let's move forward to talk about another law, that is Amagat's law of partial volume. Now let's talk about the sixth one, that is Amagat's law of partial volume. This law is very similar to the Dalton's law of partial pressure. That is, in a closed chamber, if there are number of gas molecules over here, then all the gas molecules will exert certain pressure inside it, sorry, volume inside it. They will occupy certain volume inside it. Now if we consider V1 to be the partial volume occupied by first gas, if we consider V2 to be partial volume of second gas, similarly Vn to be the partial volume of nth gas, then total volume will be equal to V1 plus V2 plus V3 plus dot 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 Vn, and that will give us summation I to n Vi. So this is Amagat's law of partial volume. Now there is a numerical problem related to this Amagat's law of partial volume. Let's talk about that. Okay. So I won't write the complete question. I'll just write what are given. Okay. So it is given that the mass of hydrogen is equal to 1.0 into 10 to the power minus 2 kg, and the mass of oxygen that is given to be 6.4 into 10 to the power minus 2, and they are put in a chamber. Hydrogen oxygen, hydrogen oxygen, hydrogen oxygen, hydrogen oxygen, they are put in a chamber whose volume is given. So volume of container is given to be 10 into 10 to the power minus 3 meter cube, and and the temperature is kept to be 473 Kelvin. Now we need to calculate the total pressure. Total pressure is equal to what? And in another case, if spark ignites the mixer, then what will be the final volume? So let me talk about the question one more time. So the question says 1.0 into 10 to the power minus 2 kg of hydrogen and 6.4 into 10 to the power minus 2 kg of oxygen are contained in a 10 into 10 to the power minus 3 meter cube flask at 473 Kelvin. Calculate the total pressure of the mixture. If a spark ignites the mixture, what will be the final volume? So this is the given condition that we need to talk about. So let's talk about the solution. Okay, I hope you understood about the question. Let's go to another page and talk about the solution. So the number of moles, first of all we need to calculate the number of moles of hydrogen. The number of moles of hydrogen, that is NH2, is given to be the mass 1.0 into 10 to the power minus 2 by the molecular weight, that is 2 into 10 to the power minus 3. We are taking this minus 3 to convert gram into kg, okay, because our question is in kg, and this gives us 5.0. Similarly, the number of moles of oxygen, the number of moles of oxygen, that is NO2, is equal to, and the mass of oxygen is given to be 6.4 into 10 to the power minus 2, and the molecular weight of oxygen in kg is 32 into 10 to the power minus 3, right? And this gives us 2.0. So the total pressure, so the total pressure P is given to be NT into RT by V. This is the ideal gas equation in case of partial pressures, right? So anti means add these two, 5.0 plus 2.0 into R. So if the values are given in kgs, then what is the value of R? That is 8.314 Newton meter per Kelvin per mole. So in this unit system, the value of R is this much. Temperature is given to be 473 Kelvin, and the volume is in the denominator, that is given to be 10 into 10 to the power minus 3. And if we solve it, we will directly get the value to be 27.54 into 10 to the power 5 Newton per meter square. This is the total pressure. This is the total pressure of the mixer. Now what if we ignite it? So if we ignite it, hydrogen and oxygen will react. Now second case. So if we ignite it, the hydrogen and oxygen will react to form water. By the reaction, H2 plus O2 give 2H2, and we'll put 2 over here to balance it, 2H2O. This is also in gas phase, this is also in gas phase, and this is also in gas phase. So we see that 2 moles of hydrogen and 1 mole of oxygen giving 2 mole of water, right? 2 mole of water. Let me talk about it over here as well. 2H2 plus O2 giving 2H2O. 2 mole, 1 mole, and 2 mole. So what was the value of the number of moles of oxygen? 2. Now to balance it, if we put 2 over here, that is 2O2, then we need to modify this equation. We need to put 4 over here and 4 over here, right? Now the number of moles of oxygen is used. We had 2 moles and we are using these 2 moles, and to use these 2 moles of oxygen, we need 4 moles of hydrogen. But how many moles of hydrogen did we have? We had 5 moles of hydrogen. That means 1 mole is still remaining. That is 1 mole is remaining. Right? Now in this case, if we apply the ideal gas equation, applying the ideal gas equation, in this case, applying the ideal gas equation, what do we get? Total pressure is equal to NT into RT by V. Now, what is the value of NT, total number of moles? So, this much of reactant is producing this much of product. So, 4 moles has been formed. 1 mole was remaining. Total number of mole is 4 plus 1 into R. The value of R is 8.314 into T means 473 by V means 10 into 10 to the power minus 3. And if we solve it, we will get 19.66 into 10 to the power 5 Newton per meter square. So this is the total pressure when the reacting mixtures are ignited. This is very simple one, right? Now let's move forward to talk about the Graham's law of diffusion. 7. That is Graham's law of diffusion. Graham's law of diffusion. So do you know the meaning of diffusion? Well, if we consider a vessel in which there are two different chambers and there is a hole between the chamber that will allow the gases from one side to travel to another side B. Now in A, the density of gas is more than the density of gas in B. So if the chamber is opened from inside, then the gases will travel from A to B because the density of gas in A is more and the density of gas in B is less. So the migration of gas from a high rho, that is high density, to low density is called diffusion. Okay, this is very simple thing. So Graham said that at constant temperature and pressure, when we keep the constant temperature and pressure, the rate of diffusion is inversely proportional the rate of diffusion is inversely proportional to the square root of its density. So if the rate of diffusion is considered to be R and the density is considered to be rho, then according to Graham's law, rate is proportional to 1 by root under rho. This is the statement of Graham's law. Now if we consider two cases, that is R1, that is rate 1 at density T1 rho 1, and R2 rate 2 at density rho 2, then R1 will be proportional to 1 by root under rho 1 and R2 will be proportional to 1 by root under rho 2. Then if we divide this value by this value by removing this proportionality constant and putting proportionality sign by putting constant, then we will directly get R1 by R2 is equal to root under rho 2 by rho 1. This is a very important formula for numerical problem. Also, we know that the molecular weight of any gas is directly proportional to the density. If molecular weight is more, density will be more. So, this equation will turn to R1 by R2 is equal to root under M2 by M1. Now, these two equations are very important for your numerical problem as well. So, when the rate of diffusion at density R1 and rate of diffusion at density R2 are given, then we can apply this formula. I'm sorry, among these four values, if three of them are given and one of them is not given, then we can apply this formula. If R1 is given, if R1 is given, rho 2 is given, rho 1 is given, and if it tells you to find out the value of R2, then we can use Graham's law of diffusion that relates the rate of diffusion with the density or molecular weight of the substance. Now, these are some of the laws that govern the ideal gas behavior. Now, those gases which follow all these 7 laws are called the ideal gases, and those gases which only follows the these laws at low pressure and high temperature are called the real gases. This hydrogen, nitrogen, oxygen, these are all real gases, and the one that we are talking about, they do not exist at all. Okay, but for ideal behavior, for proper mathematical calculation, we need to study about this ideal behavior of gases. That's all in this video. If you like the video, please share this video as much as you can. And thank you for watching the video. And don't forget to subscribe my channel as well. Bye bye.